A very warm welcome to everybody. Welcome to the IFRR Robotics Colloquia series. Today we have a colloquium on the future of robotic manipulation. And this whole series is organized by the International Foundation of Robotics Research. As always, we have assembled a panel of world-renowned experts on the topic of robotic manipulation. And we'll be trying to figure out what the future of robotic manipulation looks like. First of all, let me start with a somewhat altered quote of a book of one of our panelists, Matt Mason, who wrote that manipulation is the process of using one's hands to change one's environment. And I think we can look at these capuchin monkeys and kind of extend that manipulation definition a little bit to also use other parts of the body, like the mouth, the hands, and the feet, and possibly also tools as the stone here. Turns out that there are actually quite a few species that are capable of performing complex manipulation. Something that was thought to be reserved for humans actually is quite prevalent among animals too. And by doing a comparative study of different species and of evolutionary patterns in those species, basically people have found evidence that there is an evolutionary feedback loop between the development of complex manipulation skills and the development of human cognition. So as we discuss the future of robotic manipulation today, as we make progress towards understanding how to really solve this robotic manipulation problem, we are also making progress towards understanding the basis of human cognition and maybe even the basis of human intelligence. All right, so it's that's interesting, but maybe you say that you're more interested in industrial applications of robotics, but even there, it is kind of obvious that manipulation plays a critical role in enabling many important applications. Just imagine the volume of goods that is being shipped all around the planet every day that are still today mostly manipulated and packaged by humans. Automating that clearly can have a humongous impact. So yes, we believe that manipulation is very, very important, both in terms of scientific understanding of us humans and our intelligence, as well as in terms of economic aspects. And it's kind of surprising to realize that we don't really fully understand how to solve manipulation. There are a whole bunch of different views of how we should approach it. And I want to just juxtapose two of them right now to prepare for our panel discussion. What you see here is an in-hand manipulation skill, so a manipulation that happens entirely inside the hand of OpenAI. And this approach, I would say, is based on dynamic simulations of the interactions that you're observing here in the real world, and machine learning based on deep neural networks. So you can see that this was a landmark success a couple of years ago, demonstrating in-hand manipulation capabilities that had not been seen before. I'm going to also show you a video of a rather kind of different emphasis of a different approach to robotic manipulation. Here you see also the in-hand manipulation of a cube, but here the software actually is super, super simple, and most of the complexity has been pushed into the hand. And this hand is actually capable of manipulating the cube, as you see here, but it's also the same open loop, so sensorless skill is capable of manipulating a whole variety of objects. What you will see here is a 90-degree counterclockwise rotation, followed by a restoration of the object to its original position. On all of these 8 hands, the exact same skill is being executed, but the objects that are being manipulated are different in shape, size, and weight. So these are two different views, right? One is to kind of emphasize the software using data and machine learning, whereas here the emphasis is more on hardware. And obviously the question that we want to answer today is which of these is the right approach. And our panel, which I'll introduce in a second, represents quite a few different views on how we should approach manipulation. And I guess the hope would be that in our discussion, we learn more about which of these approaches actually is the right one. And if I can voice a little bit of a hope for our debate, it would be that in addition, we try to discuss how we can actually combine the best aspects of all of these approaches into one. Because I actually think whenever there are different ideas about something, the best idea is to bring the ideas together. And so this is kind of the framing, I guess, for our debate today, that we have 5 panelists, which I'll show you here. These are the 5 panelists. They will represent their personal perspective on manipulation. And let's hope that in the discussion we can find sort of the common ground that allows us to move towards the future. Let me quickly introduce the panel. We start with Maria Pozzi, and by the way, these are also this is the sequence in which they will present. Maria is from the University of Siena. The next presentation will be given by Matt Mason, who is from Carnegie Mellon University, followed by Frank Park from Seoul National University, then Sergey Levin from the University of California, Berkeley, and Francisco Valero Cuevas from University of Southern California. So these 5 people will give 7-minute presentations, once interrupted with questions. And the questions in the first 2 rounds of interactions will come from the special feature of the robotics colloquia from IFRR, which is the front row. These are also experts in manipulation. And we have Tamim Asfour, now it's alphabetical order, Tamim Asfour from Karlsruhe Institute of Technology. We have Aude Billard from EPFL in Lausanne, Ashish Deshpande from University of Texas, Austin, Danica Kragic from KTH in Sweden, and finally, Alberto Rodriguez from MIT. So with this, I would like to give you a quick overview, right? So 3 talks, then there's going to be a Q&A by the front row, 2 more presentations, QA by the front row, and then finally we get to the QA from everybody. There will be a link posted into the chat to a Slido website where you can enter your questions and upvote and downvote them. And I will be taking questions and interleaving them with the front row discussion. So with all of this, I would like to thank you for listening to me, and I'm excited to pass the torch to Maria.
All right, I will share my screen. There you go.
Yes, we can see it and we can hear you.
Okay,
everything's
great. Fine. Okay, so hi everyone, and thank you to the organizers, and thanks to Oliver for this nice opportunity. I will give my perspectives on manipulation with a bias on soft manipulation. So let me start by pointing out that softness is fundamental in human grasping in 2 aspects mainly. We use softness when we interact with the environment and to grasp an object, and also we exploit the softness in our hands to interact with the object itself. So in this video, we see me grasping a pen. First, I do it naturally in the most natural way. The second time, I do it without looking at the pen. The third time, I do it by trying not to touch the environment. So as we saw from the first 2 examples, we tend to exploit the environment to better grasp the object, above all when the object is, for example, small as a pen, and when there are uncertainties on its positioning. And then instead, trying to grasp small objects like a pen without actually touching the environment is something very unnatural and requires to stiffen the hand and just be very precise to avoid the environment. So based on these considerations, soft manipulation in robotics takes inspiration from a human behavior, a human way of doing, of grasping things. And so the design of soft hands is somehow a consequence of the fact that we want to reproduce a certain behavior in the hand. So while rigid hands are actually usually controlled so to avoid the interaction with the environment and to limit the interaction with objects, instead soft hands are designed to basically interact with the environment and exploit that interaction. That is not only safe, it can also be useful to really have robust grasps. And and adding soft inclusions in hands, or actually making them fully compliant, is very important also because soft hands can actually exploit the interaction with the object to actually wrap it, and so adapt their shape to the object and better, again, grasp it. So when we have soft hands, as also Oliver was pointing out, maybe the complexity of the software or the controller or the planner are reduced because we have some kind of intelligence embedded in the design of the hand. Here we see an example of soft hands interacting with objects and environment. In particular, we are seeing examples of edge grasp. This is a strategy that actually exploits the edge of a table to grasp an object. In the first case, we have a continuous motion of the hand that then wraps around the object. So we see both interactions with the environment and with the object. Then we see a hand that actually is doing the same thing. It's exploiting the environment and it's exploiting the edge, but it's doing this in a very different way, just by touching the edge of the table and then dragging the object towards the palm with the fingers. And in the third example that we see here, the hand is actually doing a motion to transport the object towards the edge and then changes configuration to grasp it. So already from these examples, we see that the design of the hand is very related then to all the other components of the grasping system. So in soft manipulation, we have really we need to really have an integrated approach to manipulation. And whenever we have, as it is often the case in robotics, when we have a simple yet powerful idea like soft manipulation, we have also struggles to implement that idea. And we need to understand, for example, which materials, which technologies, how many degrees of freedom we want to have in the hand. But then if we have underactuated hands, proprioceptive sensing becomes less easy. And then how can we plan and control hands that are maybe not sensorized, but at the same time we want to exploit their capability of interaction? And then concerning applications, we have questions about how to evaluate and test soft hands and soft manipulation, which actually opened new applications in robotic manipulation, like food handling or human-robot interaction. But then how can we really evaluate and test those soft hands and soft manipulation? And I think we have many tools and many models, and we already have some books about rigid hands. Now we are actually in the process of building a framework also for soft hands. It might be that we will take inspiration from what we already know from rigid hands, and that's for sure, but also we will need a new perspective probably to build the soft manipulation in robotics. And indeed, I think the future of manipulation is soft, not only because we will continue and we are continuing designing new hands and grippers. For example, we recently designed a hand that embeds constraints, which helps the hand itself to actually exploit the environment. But then I think there will be research on soft hand-arm systems, so the integration between what happens in terms of hand and in terms of arm. And then, as Oliver showed before, also the problem of soft in-hand manipulation is being tackled. And probably we also need to understand what happens when manipulation is done together with the environment. But then softness can be also in the objects themselves. So there is the whole many open problems, much research on deformable objects, and the softness can be seen also in the environment. So we can think about having soft environments where rigid gripper can actually go there and interact with that soft environment, because the interface between the hand and the environment is kept soft. So thank you for your attention.
Great, Maria. Thank you very much for presenting the future of robotic manipulation from a soft perspective. We continue right away, moving on to Matt.
Oh, me already?
Yes, it's already you. Surprise, surprise.
Let's see here, share screen. There we go. Share and present. Can you see that?
Yep, everything is fine.
Excellent. Okay. Well, hi, I'm Matt. Thanks for coming to the colloquium. I'm going to start with some history. So back in 1980, it was about that time that electric commercial manipulators became available that were pretty good performance. And at that point, by some of us, I mean, so I was a computer scientist. I was in grad school at the MIT AI lab. Some of us might have said, wow, this is great. The Mechis and the double E's gave us this awesome machine. It's a programmable motion machine. All it needs is programming. And so, well, we're the ones that do the programming. We're the computer scientists or the AI guys. So thank you very much, engineers. You're dismissed. Great job. We'll see you later. But that was a mistake. And I've got 3 examples here. So one is that Tomas Lozano Perez and Mike Wesley, in order to address the problem of motion planning, collision avoidance, they invented C-space. I don't remember what they were calling it originally. Maybe they didn't even give it a name. But what happened was that somebody else, another student in the lab, was reading Lanczos's Variational Principles of Mechanics, which describes C-space and gives a very nice explanation of how great it is. And, that was just in time, basically, for these guys to include it in their publications. The second example is myself. I was not quite so lucky. I didn't find out until after the publications that I should have been using screw theory or something equivalent. I didn't learn screw theory until later. And so there was a couple of mistakes in my work on compliant motion. Now, the third example is sort of the opposite side of the coin, and that is Dan Whitney and his colleagues who worked on the mechanics of assembly. What are the forces and motions that prevail when 2 bodies are in contact? And in that case, they did have a great background in the relevant applied mechanics. And as far as I know, nobody's ever identified any flaws with what they did. So what these all have in common is that they were all looking at the whole machine. They weren't just looking at the arm, they were looking at the arm plus the task. And then what they did not share in common was whether they had the relevant knowledge in applied mechanics. So then, the thesis here is that the goal is not to control this machine. If you're washing dishes, then the goal is to control the dishes and the soap or water and ultimately control the dirt, I guess. And the way that is done, the only way you can do that is to make contact between the arm and the objects. And when you do that, you're defining a little machine, right? So every time you make or break contacts, you're changing the structure of that machine. And let me give you a simple example. So this is the simplest example I can think of. Suppose you're trying to pivot a block 90 degrees. And so you put your finger on it and drag to the right, and it rolls for a little while without slipping. And then at some point, a friction limit is exceeded and the block slides the rest of the way down to the table. If you draw the kinematic mechanism model, that's below. And I had those 3 little dots are the, I forgot I was talking about the whole machine. So I forgot to put in the arm. It should be the arm plus the task. Anyway, it's just the task we're looking at here. And so it starts with 2 revolute joints. And then at some point when it slips, you have 2 prismatic joints as well. And so the mechanism has changed its structure in the middle. And you may not even know exactly when, because it depends on the friction limit, which is somewhat uncertain. So it's a little machine, but it's a weird machine, right? The kinematics is varying perhaps in a not clearly predictable way. And then this is just the rigid body model, right? There's lots of other things that you want to worry about. Maria was just talking about soft stuff. So you want to be able to model the flexures and the flexible links. And then if you're doing dishes, actually, you got to worry about fluids. So, maybe someday we'll have a field called wet robotics, or maybe we already do, and I just didn't know. But so you've got these weird machines, and I think so what are the implications for the future? To the extent, I'm going to say that to the extent that a robotic manipulator can control it, the world is a big machine, and the robot's a part of that big machine. At any point in time, the relevant part is just the bits of the world that the robot is in contact with, and that's time varying. But at any point in time, you've got some little machine that the robot is controlling in order to accomplish the task. And so looked at this way, manipulation is the design and fabrication and control of a sequence of small machines. And if it's an uncertain task, if it's something you haven't done before, you're doing it improvisationally, right? You're doing it with the stuff that's at hand, literally at hand. So it's kind of an amazing improvisational mechanical engineering thing that's going on there. Looking at it this way, the question that pops into my head inevitably is to wonder whether robotics is engineering complete. Is it possible to really solve robotics without solving all of engineering? And I think the answer to that is no, it's not engineering complete. I'm sure we can think of things in engineering that are not so relevant to robotics, but it might be a substantial fraction. It might be kind of engineering complete-ish. So yeah, the future, how do we get there? Well, first off, let us not repeat history, okay? We're lucky when we tried to dismiss the engineers, they weren't listening. They just laughed at us. Okay, they're still around, so that's good. This is a slightly different view of machines than you might get from the curriculum, at least the one that I'm familiar with. I've seen just a few papers on variable structure machines. I think they're very important. We've been working on it in my lab, so these videos are from some recent papers on the enumeration and control of contact modes. And then there's the other weirdness, which Maria was talking about, and I'm sure we'll have more discussion of that. One thing is specifically to address is machine learning. If robotics is engineering complete-ish, then the question is, can a robot really learn, all of engineering? And I don't think it can in its lifetime. I think evolution is an existence proof that it is possible to learn all of robotics or all of human manipulation, I'll say. But I think the vast majority of that is going to be nature, not nurture, and that robots should be born with almost all of this already in their heads and just learn a little bit more. So I think that's my whole talk. Yep, here's some references for some of the stuff that I mentioned. And I just want to thank the people that helped out, and that's it.
Great, thank you so much, Matt. And thank you in particular for already setting up some discussions about the tension between hard robots, soft robots, and machine learning, nature versus nurture. Fantastic. And we're going to continue right away with Frank.
Hey, thank you. Let me share my screen. Okay.
Works.
Great. All right. First of all, thanks to Oliver for putting together this amazing cast of speakers and experts on manipulation and learning. So, I'm speaking after Matt, who figuratively and literally wrote the book on manipulation, and Sergey is currently writing the book on reinforcement learning. So, frankly, I'm wondering how I got invited, but I'm here. And since Oliver asked us to, pay special attention to the issue of sort of learning versus model-based approaches to manipulation, I think I can best contribute to this discussion by focusing on the modeling aspects. Specifically, what's the state of the art? But maybe more to the point, do we even need to bother with the state of the art given the so-called magical powers of machine learning and data-driven methods? So the first thing that I think we should get out of the way, and I'm sure everybody will agree on this point, is that model-based and data-driven approaches are not an either-or proposition. They go hand in hand, and they complement each other. You know, Aude Biard is here, and I think she got it exactly right when she said that, you know, in her own recent IFRR talk, that, you know, we need to start with models. Important caveat, valid models. And when the models don't quite do the job, then to complement these with data-driven methods. And to that, I might maybe add, you might want to consider using data-driven methods to learn the model parameters. So with that being said, you know, let's look at the models. Let me just first begin by clarifying that by model, you know, I mean, you know, equations of motion, you know, that are based on some mechanics principles, you know, not tables or neural networks. Although I'm aware that other people might have, you know, broader meanings of what a model is, and I'm fine with that. So the first thing that needs to be said about a model is that a model is not reality, but it's an approximation of reality. The second obvious thing is that a model is only good as the fidelity of its parameters. So these are all, you know, obvious facts about models that we learn in any introductory class on modeling, right? So what are the challenges? Well, you know, mechanics-based robot models are complicated. The equations and motions are complicated. They're highly nonlinear. Right? Model identification is hard. Lots of DOFs, lots of constraints. Measurements can be expensive. They're noisy, incomplete. You know, finding sufficiently exciting trajectories is not easy. And there's a lot of unmodeled dynamics that I'll talk about in a bit. So it's hard. So, you know, given these challenges, I think there's a real temptation to abandon these traditional dynamic models and just run to data-driven models. So, you know, here's a sort of very loose hierarchy of you know, models. So, you know, just concerning for the most part, robots that are mostly rigid, allowing for some elasticity in the links and joints and driven by electric motors and so on. But let me just go through this hierarchy a little bit. So kinematics, right? Kinematics of open and closed chains, it's a solved problem. You know, if you need to solve the forward or inverse kinematics, you know, there's no reason to be actually collecting data and training neural networks. You know, about 30 years ago, there was a fad where a small community of people were actually solving forward and inverse kinematics using neural networks. And, you know, when I get a paper like that, you know, you immediately file it into the circular file. Kinematics of contact, right? How contact between two hard objects, you know, moving relative to each other. Again, you know, it's known, Montana's contact equations. Calibration, identifying kinematic model parameters. Again, you know, all done. So basically, you know, for prehensile manipulation of rigid objects, you know, for which we know the shape and all the properties, we have all the models that we need. Dynamics. Again, formulating the dynamics, straightforward. Evaluating, integrating, differentiating the dynamics, also doable. You know, the latter is especially useful for right, optimizing motions. So these were all done in the very early 1990s, and these motions are generated all in near real time, right? So not much issue there when it comes to dynamics. Dynamic model identification. Okay, this is still not yet a solved problem, right? So, you know, some people think it's solved, but actually you have to take into account that, you know, we don't have these very expensive sensors and robots are getting more complicated. So it is more challenging, but there has been some recent progress using geometric methods in particular. So, you know, here's a, you know, just snapshot. So, you know, using sort of the new results in geometry and modeling, you know, now you're able to use like very simple, you know, we a balance board and a Connect to actually reasonably accurately identify you know, mass and inertial parameters for humans and high degree of freedom humanoids. Now things get a little murkier, you know, when you go down to the level of actuator dynamics, gears, tendons, elasticity, friction, and so on. So, there are working models that exist for systems, but, the systems can't be too complicated. And, you can't have, for example, series elastic actuators, which really complicates things. And of course, what Maria mentioned, soft robots, right? We need new models and tools, beyond the usual finite element methods and pseudo-rigid body models. So, there's a lot of theory, but I don't think we have the computational algorithms yet. So that's certainly an area that we need to. So, choosing the right model. Obviously, this is the big question, and to a large extent, it depends on the application context. For legged robot locomotion, simple models with good control laws seem to work. But Sami Haradin likes to point out that, for complex, dynamic manipulation tasks, the last 5 to 10% of the dynamics can be really critical. And obviously the environment in which the robot operates, also clearly important, right? So just maybe tell you a little bit about, my 2 recent experiences trying to make this choice. Do I go model-based or data-driven? So, the first one is actually, they asked, I was working with a company developing collaborative robots, and they wanted to do collision detection without using joint torque sensors because joint torque sensors are expensive. So again, here, there are well-known sort of model-based methods, and they work very well. But they do require a lot of tuning. You have to go in there and identify the model and tune a lot of things. On the other hand, learning-based methods, they have the promise of, just collect a bunch of data and then there's some tuning. Well, it turns out, collecting data, I didn't realize that my student was engaged in such a dangerous activity, but, collecting the data is, quite a bit of work. But anyways, so we find that, well, it's not conclusive, but using the robot dynamic model in conjunction with machine learning algorithms seems to work reasonably well. But I think it's a fair question, model-based versus learning-based. Which is easier, right? So there's some tuning. Is it really some tuning, or is there a lot of tuning? Another sort of experience with this machine learning versus data-driven is we were working with Naver Labs. They developed this fabulous tendon-driven robot, and so we work with them on doing sort of motion control for impact motions. And the dynamics is really complicated by the tendons and the friction. Tendons are just really horrible to model. So again, here, do you try to use existing tendon models, or do you use machine learning? So we opted for the latter, and it seems to work well. And just a brief aside, adaptive control is something that seems to have kind of fallen by the wayside. This was kind of a hot topic, and in some ways it's engaged in kind of learning. And while I'm mentioning this, I would also maybe point out that there seems to be missing a sort of a unified framework for hybrid force, position, and impedance control. That I think is very important for manipulation, especially for closed chain systems. Anyways, so I thought I would just throw out some sort of random reflections and questions that I had in thinking about this. And I guess the first thing is that people seem to be just giving up too easily on model-based methods and going for the sort of the easy money of data-driven machine learning methods. And I know this is driven by the pressure to publish and other factors at play, but people don't seem to be aware that model identification has come a long way, and you can obtain pretty robust dynamic models using very cheap off-the-shelf systems, sensors. I can't really think of any good reasons to be using, Gaussian process dynamical models or other stochastic dynamic equations in lieu of mechanics-based, models. The generalizability doesn't seem very good. I think it makes much more sense to use classical methods, mechanics, and to add noise where appropriate. Augmenting mechanics models with data-driven methods seems a good idea, especially when you're dealing with things like elasticity and friction and deformations. New models are clearly needed for soft robots. For example, there's a lot of geometry of, how inelastic curves and surfaces and volumes evolve, and I think we need to develop computational algorithms that exploit those results. Now I know Alberto is also here. He's been thinking about some of these questions, but there's a ton of tactile information to be gathered in grasping for example shear and normal forces that you can now collect using these these new flexible sensors. And obviously CNNs are very good at processing, extracting the important components from these high dimensional, these nonlinear coupled signals. So and these in turn may help us to develop sort of useful models of how we use shear and normal tactile force measurements that are processed and used by our brain in these fine manipulation tasks. And I think it'd be nice, to see in my lifetime, practical and commercially viable robots, that actually perform useful tasks, that people actually want to buy. And of course, manipulation is the holy grail, right? But it means reliability and cost are also important. So deep learning has obviously lowered the barrier. And so no more years of studying mechanics and planning and control and screw theory. And they may hold advantages over model-based methods when it comes to sort of mass production and usage. But obviously, I think we need people to study this a little more. Now, the last thing that I'd like to sort of reflect on is that this occurred to me while I was watching Joelle Pineau's 2018 NeurIPS plenary lecture, where she asked a general question, and I know Sergey is going to be maybe coming up next, but how replicable and reusable are reinforcement learning methods in general? And one of the interesting things she pointed out is that reinforcement learning is the only case of machine learning where it is acceptable to test on your training set, right? RL methods require just huge amounts of data. Jan Peters likes to say that our RL can require more trials and data than one can generate in the lifetime of the robot. Simulation obviously helps, but not always. And I've seen more than my share of these machine learning papers of the form. I tried this network on this data set and beat the state of the art by 5%, but I really can't explain why, and I can't guarantee that it will do the same for your data set. And so I wonder if it's time to ask similar questions about RL in the context of robotics, and if there's a way to test and compare robot learning algorithms in the context of manipulation against each other in a more fair and consistent way. I hope I haven't gone over time, so I will conclude with that. Thanks.
Thank you, Frank. Just a little bit over time. Thank you also very much for already getting us started on this mission of integrating the different branches and resolving the tension between the different camps in our research area. Yes, so these were the first 3 talks. And now we're handing over the word to the front row to ask some questions. Wood, maybe you want to get started?
Sure. So first, thanks a lot. It was very, very interesting. Tons of questions. But I'll start just with one. So what I gather from all three talks is that somehow the model will put the perspective into what we choose to do with the manipulation. And it seems that it's fairly dichotomic. Matt presented a way of doing it where you place yourself in the object-centric viewpoint. And then you can look at the manipulation as the object and the hand. When we control our hands, we often control for all the fingers, sometimes coupled, sometimes not. when we control for manipulation with 2 or 3 robotic arms, we often think of separate arms and then we bring them together, or we think of it as separate arms with respect to the objects, but each time it's a different perspective. And then Maria told us about soft robot control versus hard robot control, as if these were also 2 dichotomic worlds. And nobody, well, except for Frank, mentioned really about deformable objects. We saw rigid objects, but this is also possibly another physics. And then up we go into another type of model. But the world is a continuum. And is this not something for weakness in robotics, that we have this dichotomic view, that each time we choose a model, we choose a perspective, and then off we go with different set of equations? How do we go about transiting across those? How do we go about picking up an object with the hand first, and then we move it, and then we hold it with the entire arm? Would we have to change entirely the model and the perspective? How do we go about picking up an object from an object-centric perspective, and then we have it in one hand, and we manipulate, and then the 2 frame of reference merge? And then what if the object dissolves and becomes soft? How do we go about doing a single representation for all of that? So my question is, do you think that we are wrong in separating these models into separate books?
So this is probably directed at more than just Maria, Matt, and Frank, or I guess Maria, Matt, and Frank should,
but
should try to answer.
I mean, I will be happy to hear from all 3 of them.
Who wants to take a first stab at the answer?
I can. Okay.
Yeah, go ahead, Maria.
No, okay. No, I think having everything separated is not the good way to go. I mean, so it's okay to merge sometimes. Even, for example, when we talk about models for soft robotics and models for rigid robots, there are cases in which we can actually, for example, approximate a continuous robot with a open kinematic chain, and then maybe estimate the parameters of that kinematic change based on data-driven algorithms. And so we can actually, I think the way we have to go is to merge approaches and use what we need when we need it. And yeah, so it's not a dichotomic way, but sometimes what I wanted to say with the slide about rigid hands and soft hands is that there are many things that we can actually try to, I mean, we can try to extend the rigid models to include compliance, to include stiffness, but then it's not always said that we will get where we want. And so maybe sometimes it's possible that we need another perspective, and maybe instead of thinking of a hand as a set of kinematic chains, we might think about it as something different, like, I don't know, approximating a full complete hand with just a direction of closure, for example, or similar things.
Matt, you seemed like you wanted to also answer.
Yeah, let's see. I think it's a good question. I guess I have 2 responses, which is to some extent I was trying to capture, you know, I might try to convince you that I was going after that issue, that you're doing one thing and then another thing and another thing. So the nature of the mechanism that you're controlling is changing. So, you know, the example of picking up a water bottle and then holding it against your body, right, is changing the mechanism. And that's what I was trying to address. But I'm not sure, you know, the world is a big and complex place, and there are limits that we haven't run into yet, and I'm not sure. So my other answer to your question is like, yeah, we should do something about it, and I don't know what exactly.
Okay, so we have 2 more raised hands by Alberto and Tamim, and maybe we'll end it here to hear after you guys have asked your questions or comments, to go to the final 2 talks. And before we do that, I also want to take 2 questions from Slido. So Alberto, please go ahead.
Thank you. I just wanted to sort of ask a question I kind of see two philosophies within the three talks that we've heard so far with respect to building robots. So one, I would say, is maybe more embraced by Frank, where you want a robot to do what we intended to do, right? So I want to build a robot that if I tell it to go here, it does there. It sort of bends to the will of the roboticist, and it does it precisely with the right timing, the right velocity. And then there's the philosophy where we build a robot that bends to the will of the task, right? So I really don't care sort of what the tensions in the tendons or the torques are. I just want the Rubik's Cube to sort of twist and sort of conform, which opens up sort of the design space, maybe to softness, to things that might be more difficult to model, but that could facilitate some of the aspects of the task. It could also complicate some of the aspects of our understanding of what's going on. And I just wanted to sort of get your opinion versus those two philosophies. Can actually be combined, or are they sort of really two dichotomies?
Yeah, good question. Who wants to try to answer this? Well, if nobody wants to answer it, I'm gonna seize the opportunity. So please, somebody try to answer. Or Tamim, do you want to answer it? Francisco, you have to unmute.
I could talk about it after I finish, but yes, I think this is very important to consider the syntax of the world as well as the composition of the brain and body interaction. So I'll speak to that in a little while.
Okay, so I guess that means we'll go back to Alberto's question after we've seen all the presentations, because there's more relevant stuff coming up. But I think it's an important question, and please, Alberto, raise it again after we've seen all presentations. Tamim.
Yeah, actually, I have a question regarding what's specific about manipulation in what you described, because you're starting discussing learning-based versus model-based, but this is something you can apply to any topic. So, what I maybe would like to ask. What's specific for manipulation, because we're talking really about manipulation, and whether you think that, and also maybe back to the question of Oud, that we already have solutions for certain parts in manipulation, like very nice sensors where we can, Alberto, can detect tactile information or capture object properties. We have nice controllers. Don't you think that the progress in manipulation is actually limited due to the fact that we're not able to put these things together because we don't consider too much transitions between different phases in manipulation?
Were you asking somebody specifically or just everybody?
Everybody.
Seems like if you ask everybody, nobody feels asked.
No, maybe I can say something like, manipulation systems are complex, and so as we all know, we have the sensing part, we have the control part, we have the design of the hand. And so, yeah, I agree that probably we need a more integrated view of the whole system instead of separating the design or against the sensorization, and then the control, and then the planning, and then and what happened with the soft manipulation is that all the boundaries between these different aspects of the manipulation task became a bit more blurred, because everything is very related to the design of the hand, and so based on that, you really need to do the choices that come after. And so, yeah, I think it's important to really think about each component and then try to integrate them.
I think what's more important really to think about what happens in manipulation and how how transitions between different, let me call them phases, in a manipulation task should be. And this is different when you manipulate, cross manipulate soft rigid objects or deformable objects with soft or rigid hands and so on. And I would claim, I mean, I know I have to ask question, but maybe a comment that really this is something where more efforts and more attention should be put on.
So you meant in the phases of the same manipulation task. So from the approach really to the grasping. Yeah. I agree that. Yeah.
And this extends, by the way, to the design of the robot. Why do we have only rigid hands and soft hands? Do we have any combination of the two?
Yes, of course.
There are.
Not so many, though.
I would say all hands are a combination of the two. There are no purely rigid or purely soft hands. But let me try to sneak in some questions from Slido, because some people have been waiting, and I think it's more entertaining for people out there if they hear their own questions being answered. Let me direct these questions actually to people, to specific people, members of the panel. The first question is by Anonymous. How much have the commercial manipulators or robotic arms improved since the 80s? And I think this is a question for Matt, who was talking about the 80s in his presentation.
Yeah, they've improved a lot. When we started the panel, the question was, robots reaching human level performance. And so you might ask the question like, where's the threshold? Where did robots become mechanically good enough and that we could start worrying about the programming, planning, and so forth, and say that that's the real problem? And the argument, the thing to look at there is teleoperation. So, the argument, the mechanics has reached that certain point might be illustrated by the Da Vinci, which can do surgery, except it lacks the perception and intelligence that has to be provided by a human being. So that hasn't stopped anybody, right? So the development of the mechanics of the arm just goes right on, and there are arms out there that are superhuman in certain on certain tasks. So yeah, I mean, that's continued unabated, and we have arms that now that are way better than they were in the 80s.
Great, thanks, Matt. Let me put together two questions that have been asked and that are highly voted. One is by Kostas. Should the community aim to outline principles for when collecting data plus some tuning requires more or less effort than heavier tuning of models by an expert? That is one question, and I think it links to a question by Anonymous. Wouldn't model-based versus data-driven depend on the problem where we actually are addressing? In particular, animals can manipulate without being physics experts. So I think both of these are maybe a little bit towards Frank's talk, right?
Yeah. Yeah. So I agree. It's very problem dependent, and the answer is that to me there's no clear answer. Given a particular problem, what's for example, that collision detection example I showed you. I wrote a paper. In the paper, I claimed that using the model plus the data-driven method works better. But confession, I'm not sure I believe that myself, because it was a lot of work. They say machine learning methods don't require as much tuning as model-based methods. Again, that's debatable. Collecting the data is a lot of work. But what is important is, I think, generalizability. If you have these, data-driven plus model-based methods, can you apply it, to more general tasks, to more general robots working in different task scenarios? And we don't see too much of that being addressed in today's literature, I think.
Okay, great, thank you. Let's close this intermediate session of Q&A, and let's hear the final two presentations, starting out with Sergey.
Okay, let me get the screen set up there. All right.
We
Is
see
everyone
it.
able to see it?
Perfect.
Okay, great. So yes, I guess no surprise, I'm going to talk about learning manipulation skills. I'll start off with something that I'm a little concerned about when it comes to robots. I think if we want a robotic system that does one thing really well, I believe we basically know how to build that already. Not for every single thing, but for a lot of things. If we need a robot that does one thing repeatedly, we kind of have pretty good ideas about how to get started. The trouble happens when we want one robot that does a huge variety of different things. Because if each of those different things requires a whole lot of manual effort, a whole lot of manual engineering, essentially the trouble we run into is that the engineering burden of designing a more general purpose robotic manipulation system just explodes. And it's not unique to manipulation. This is actually true for any embodied system that has to act in the real world. This is actually, one of the most common failure modes for autonomous driving systems. Just the complexity keeps exploding and growing and growing and growing as there are more situations you have to deal with and more manually designed components that you need to build for every possible eventuality. And manipulation is a million times harder than that because with autonomous driving, of course, all you're doing is controlling a vehicle. Of course, in a wide range of situations. A general purpose manipulation system has to control arms and hands in an even wider range of situations. And the pictures I have here actually idealize. The real world looks more like this thing on the right. It's a complete mess, and you have to deal with whatever that mess throws at you. If you have a system for putting a dish into a dish rack in a kitchen, it also has to handle the case where you drop the dish, someone spilled a bucket of water on the floor, and the dish rack is not where it's supposed to be. So there's a huge range of skills you need just to support the one skill that you want to do. Digging more into the nuts and bolts of the engineering problem, I think a lot of the issues that we start running into when we try to design robotic systems for the real world, for open world situations, is leaky abstractions. We end up building components to solve individual parts of the problem. That's a very reasonable thing to do as an engineer, but our abstractions always refuse to cooperate with us. So we might have a perception system, something that does state estimation, something that does modeling and prediction based on that estimated state, planning based on that model, low-level control based on that plan, and so on. But if one stage in this pipeline breaks down, if your state estimator isn't quite cooperating because now someone gave you a different object you're not used to, it doesn't really matter how well all the downstream components work. They're already out of luck. They're not going to function because something upstream is failing. Robotics is not the only discipline to encounter this issue. In fact, I would argue that any system that deals with the real world encounters it, and certainly computer vision encountered this problem and struggled with it for many decades. Doing things like building pipelines and initially trying to invert the image formation process, but later on building pipelines consisting of tiers of different feature representations to try to abstract away the problem, try to build those abstractions manually. Today, we don't do that in computer vision. Today, the solution to computer vision is to train the system you want for the task you actually want to solve. If you want to recognize objects, you train it, you optimize it to recognize objects from the pixels. And that works better. And it works better because it removes the need to hand engineer all those abstractions, and the same exact code can solve many different perception problems. A colleague of mine once mentioned to me that he thought it was really odd when he was consulting for a company that an engineer there wanted to train a giant neural net to solve a problem that he thought he could solve with some manually designed edge detection and geometry method. And he was right, he could solve it that way. It's just it was easier to grab the same code that trains the giant neural net and solve that perception problem that way. Even if it was a more complicated solution computation, it was easier from the engineering standpoint. So I think that's what we're going to see in robotics. What we're going to see is that end-to-end training for manipulation skills will end up being a method that gets us a lot further for these general purpose systems because it removes so much of that engineering burden. Not because it's necessarily easy to use for any one task, but because the same system, the same code that you build for one task can be readily used for others. Now, of course, this is not without its challenges. And in a sense, we can think of what learning does. It trades off the burden of hand engineering systems, but instead replaces it with the burden of getting data for those systems. And I think one of the big challenges that we need to overcome to make this stuff really practical is effectively reusing data. So a lot of the successes we've seen in machine learning in other fields have been driven by the availability of large standardized data sets. So if you want to build a computer vision system today, you don't start collecting your data from scratch. You take some existing data set, ImageNet or MS Coco, you pre-train on that, and then you collect a more modest amount of data for the thing that you actually want to do. And I think we need to see that sort of thing happen in robotics. So that, the right recipe probably looks something like take a lot of data from stuff that robots have done before, use it to train up the best controller that you can, and then maybe fine tune it with a little bit of additional data collection. So we need things like algorithms that can actually utilize prior data. If we're talking about reinforcement learning, this means offline reinforcement learning algorithms. We also need strategies for collecting data that are fully automated. And that's actually something that I want to show you. I'll conclude with a few videos. Robotic learning is something where I think there are a lot of misconceptions about what's possible and what's not possible. A lot of people say that you need, thousands of years of data collection for RL. That's not true. You don't. You can train RL policies just fine with amounts of data that are very feasible in the real world. Here's a robotic manipulation task. The task is to pick up this object, reposition it in the hand, use the fingers to manipulate it into a desired pose. So the end goal is a particular pose for this object. The way we're going to learn it is fully automatically, without any human intervention. We're going to simultaneously learn multiple tasks, tasks for repositioning the object in the hand, and also tasks for recovering when something fails, which involves going back in and picking it back up. And here's the training process. This is the entire training process. Of course, it's sped up. It takes about 40 hours, but that 40 hours is completely automatic. So initially what the robot is doing is it's just figuring out how to position the object in the bin, then it's figuring out how to pick it up, and then once it's figured out how to pick it up, it's reorienting it in the hand. It takes a while. You need a fairly robust robot, but you need robust robots for the real world anyway, but it's completely automatic. All we do is we turn it on, we go home, come back 40 hours later, and it's actually learned to do the task. It doesn't take thousands of years, it takes 40 hours, and it takes, once training starts, basically zero human effort. So there's a lot of hard work, but during the training process, it's robot hard work, not human hard work. And we can do other tasks too. We can, pick up this connector, for example, and plug it in here. The pickup failed, but that's okay because the robot can just try it again. And again, trained fully automatically. This one I think took about 64 hours, and then it can do the whole task. We can scale this thing up. If we get more data, the capability increases, and that's what we want to see. So for example, if we can train up a robotic grasping system from images with, in this case, it's actually several months of data collection, which is a lot. But out of that, you get a robotic grasping system that can grasp objects from monocular images. To my knowledge, this is the best monocular image grasping system that I've seen. So it gets a success rate of 96% on a very difficult test set involving basically every type of object we could find. And we can readily scale up the system to a wide range of tasks. So this is work that just came out recently, 2021, where we basically took the same principle, but applied it to solve a huge range of different tasks in real world settings. I mean, these are all tasks that are kind of tabletop manipulation. They all involve basically repositioning objects, but the range is a lot larger. The method is essentially the same, with some additional machinery mostly added for sharing data across tasks and also detecting whether the task has succeeded for the reward function. That's where a lot of the additional innovation was needed. All right, yeah, thank you very much. That's all for my talk.
Wonderful, Sergey. Thank you very much for showing those impressive results. And yes, it's true. 40 hours, that's, probably is quicker than it takes a human to engineer the problem. Next is Francisco.
Unmute myself and share my screen.
Good ideas.
Okay, is it okay?
Yes, we can see you perfectly.
Well, thank you. Thank you, Oliver, for the invitation. This is a great panel that has actually touched upon many issues that are very relevant to where we are going with manipulation. And so what I wanted to do is understand what is it that we could or should learn from the biology to enhance the future of robotic manipulation. So there are three concepts I want to share with you. The first one is to actually make that conceptual distinction that grasp is not manipulation, right? So grasp couples an object to the forearm, whereas manipulation actually dynamically acts on the object with the fingers and fingertips. This has been sort of in the subtext of what we've been discussing, but I think it's important to make that distinction. And along these lines, one of the things that I've been working on is a definition of quote unquote dexterity. And what I've done is I've called this the ability to dynamically regulate the direction of fingertip force vectors to control instabilities, in the sense preventing the buckling of a spring. So this is one of the particular implementation of the system where we're actually asking a human, how good are you at manipulating? So the idea is to compress a spring that's prone to buckling and see how you hold it there. And of course, a person can do this, but actually it's deceivingly simple because it's actually a very difficult task where you actually go to the limits, to the boundary of instability. And so to me, it's interesting to understand what is it about brain-body interactions allow us to act dynamically on the world. And one of the things that you can do is you can get under the hood and actually look at the variability that you see during the task. And you actually see how you handle the instability, as opposed to how much instability you can handle. And here, this is kind of a poor man's attractor reconstruction, so that you see that the brain-body system is actually implementing an attractor that enforces the instability by postponing the bifurcation and so on. So this is becoming a clinical tool. And so the question is, who's controlling? Who's in control of this hand that is doing weird things? And we've done studies, fMRI and others. And for example, what is the communication between the motor cortex and the muscles of the finger when you're compressing just a rigid object or a spring, but actually not at the instability level? And what we actually see is that when the going gets tough, the brain actually defects. The brain, extinguishes its direct connectivity with the muscles, right? So then who's driving? Who's doing this? And what this does is it makes us ask, okay, so you do need a brain to be dexterous. And by brain, I also mean a centralized controller. But actually, sensory motor delays and noise prevent fully centralized systems. And interesting, in biological systems, it seems that older, more peripheral structures like the spinal cord which are also present in other animals that are very dexterous, like Oliver was mentioning. So these are likely involved. So then what I'm saying here is that we should be explicit about hierarchical versus centralized control, right? And actually in nature, we see these distributed hierarchical controllers essentially everywhere. There are many animals that don't have a brain or have a distributed brain. So you could have the high-level controller, but you need a middle layer, a middleware, a low-level controller that is actually dealing with the immediate system dynamics, which could be hard and soft. And actually many of the controller properties, viscosity, elasticity, deformations, etc., those are actually built into the hand itself or the object, as was mentioned before. And we are working in the context of, like Frank was mentioning, tendon-driven systems. That is what the brain is actually controlling. So I actually wrote a book on that allows us to understand how to do that. And so then if we take a step back and say, well, we should be able to build one, since we know neuroscience, we know physics, we know mechanics, etc. So what we've been doing is we've been using neuromorphic systems, essentially FPGAs that are programmed to behave as neurons, implementing the simplest of spinal cords, which is just a stretch reflex with electric motors pretending to be muscles while controlling a hand. So in the particular case of the simplest spinal cord, you have these reflex pathways that are running all the time autonomously. And this is what gives you posture. This is what gives you muscle tone. And they're always running in the background. And so what we've done is we've implemented these kinds of systems. And the fascinating thing is when you build these systems, they just work. So here you have a backdrivable, stable finger, quote unquote, that is just sitting there on your tabletop because it's implementing the simplest of neuroscience lessons. And what we've done is we've extended these to actually act on the physical human hand. This is actually a cadaver hand being actuated by these neuromorphic systems to really understand the ugliness of viscosity, elasticity, hysteresis, etc. So what we find is that moving smoothly and accurately is actually quite difficult for the nervous system itself. And that's after millions and millions of years of evolution and co-evolution of brain and body. So it begins to explain why the problem that we're trying to solve is quite complex, right? But biology gives us, like Oliver was saying, an existence proof, right? And so the next thing is, okay, so if you have such a system, if you were born into the body you inherited from your parents, how do you actually learn to use it? And this is what Sergey and others have been talking about. So what we've been doing is we've been trying to understand how is it that you can develop bio-inspired algorithms for autonomous functional movements in a tendon-driven leg or finger, that actually takes 5 minutes to do. It's autonomous. It's all in hardware. There's no simulation involved. There is no explicit modeling. And so here's a short video of this just floppy finger or leg. And the task that we're trying to do here is to propel a treadmill. And so we give it 5 minutes of motor babbling, where we actually try to create a bad inverse model of the situation. And after 5 minutes of training, and here you're actually reading the joint angles when you give it random motor signals. And after that, you actually have the system use very light reinforcement learning to say, okay, try to propel the treadmill. And every time you run it, you get a different answer. Actually, you're learning motor habits literally at random, which is not unlike what happens in development in children, where you're born into your own body, you're a young animal, you got to figure it out, and sometimes it works and sometimes it doesn't, but you actually end up creating motor habits. And so this G2P algorithm, general to particular, as we like to call it, creates suboptimal but useful motor habits. Of course, optimization is a wonderful engineering tool. However, it seems that in biology, and there's some papers that point to that as well, useful yet suboptimal motor habit seems to be what's happening. So that's a lesson that we should also learn from. And so the G2P algorithm in robots demonstrate bio-inspired autonomous learning from limited experience. And related to this, some aspect that I haven't heard too much about is this idea of the sensory side. And how, Matt, I think, was very eloquently pointing that the fact that, there is the environment, there's the world. And so actually you can extend this, and how can we give robots a sense of self? And actually this sense of self actually comes from the interaction with the environment through what we call the sensory motor gestalt. So the idea here is very simple, which is that acting in the world is locally simple, but globally complex. So for example, if you're in a particular situation, your sensory state that you've learned allows you to recognize, okay, I'm sitting down. Well, from here, I cannot start swimming. For me to start swimming, I have to transition to getting up. From getting up, I have to transition to walking. I have to transition into the water, etc. So this applies to, the whole body, or even the hand, right? If you're in power grasp, you can easily go to lateral grasp, and then to hook grip, but you cannot really jump from power to hook necessarily. So this idea is actually saying that creating, exploring, navigating, and extending this sensory motor gestalt is like all together. And I appreciate how people have been building up to this, and the questions that were asked before were very good, where you have a high-level controller, a low-level controller, actuators, your body, the object, the sensor, the task, active sensing, which is model updates on the fly, the environment, the syntax of the task, the intention, and the high-level controller, etc. So to me, this is what kind of we should be learning for the future from biology. First is like, let's focus on full-on dynamic dexterous manipulation. There's beautiful work that was shown earlier in the talks. I love that. We need to move to manipulation. And let's actually exploit the fact that hierarchical and distributed controllers work in biology. And also, don't let the optimal be the enemy of the good enough. And then actually, we may be able to find a way that we're acting in the world is locally simple, but then it builds up to be globally complex. And of course, there's an amazing team of people that I work with on these kinds of problems and their funding sources. And thank you so much.
Thanks a lot, Francisco. And it's kind of motivating and inspiring to see how parallel, I guess, the developments in biology and or biological manipulation and in robotic manipulation are, and how many connections there are. And obviously, that's why we've invited you. Wonderful. So now we've seen the 5 panelists give their presentations, and we can now roll up the sleeves and really get into the little details here. Who would like to get started? Maybe one thing before we get started, there was a question in Slido that was a clarification of Francisco's presentation. The question was whether the subject can actually watch the spring while compressing it or not, and whether it matters.
Actually, we've done that study where you can do this eyes open or eyes closed. And if you do it with eyes closed, you're actually marginally better. And the reason is that we're actually targeting these low-level, short latency processes. So as soon as you engage the visual motor loop, that's 120 millisecond delay minimum. And as you know, delays are bad for control. And then what happens if you actually anesthetize the fingertips, so you don't sense, but you can see, you're way worse. So
Great.
Tactile information is very useful.
Great, wonderful. I think Dani has agreed to kick us off, right?
Yeah, well, I can try if I can make myself easy to understand. So regarding the last two talks, I think, so thank you so much for the presentation. So I think I would like to somehow relate the question or to both of these talks. The first one regarding that computer vision community has learned how to do things differently. I do agree that some things are better, but we still haven't solved the big problems of having robots freely moving around and doing actually the interaction and manipulation. And this is something that we are talking about today. So in computer vision community, we learn the structure of the world from images, and that information is usually very structured because we make the world. Now in manipulation, something else happens, right? The robot is making its own world by interacting with the world, and it has very different sensory capabilities still to what we humans have. So the structure of the and the knowledge representation that occurs in that system through interaction is very different from what the humans are doing. Of course, it has to do with optimality. I mean, the robots maybe can achieve the same goal, but very differently. However, ultimately, I mean, if the robot is spending 6 hours of removing dishes from the dishwasher, we humans will not accept it. And the system may not be able to explain what are the reasons for actually taking that long time. So I have a little bit I don't completely understand, why do we believe that robots, when it comes to then multimodal feedback, when we take into account the embodiment and so on, can actually do a structured representation of the world that can also be communicated to humans just because computer vision community maybe managed to do it? Is it possible to do for interactive systems?
I can start with that, okay. So I think this is actually, to me, this sounds like a very convincing argument for general methods, because if we're concerned about perception that is not just cameras, and we should be, because we should be using other kinds of perception, then general algorithms that make minimal assumptions are going to be easier to use, and they're going to be more effective, and they'll work better under realistic constraints, which include engineering time. And we've actually seen this in machine learning. There's a reason why almost all areas that are performing passive perception now are using deep neural nets, because the same basic technologies that are developed for perceiving with one modality can then be used for another, like speech recognition, NLP, and so forth. So I think that the fact that we'll have to deal with different modalities is actually a great argument in favor of using general purpose methods that don't require a lot of engineering for each domain. Now, in terms, I do strongly agree with you, though, that manipulation is not the same problem as vision, and the interaction part does introduce enormous additional challenges. That said, I do think that there are a lot of parallels in how people are thinking about the intersection of model-based and learning-based reasoning in robotics now, and how people were thinking about it in computer vision decades ago. I have to make a confession, I was actually trained as a computer graphics researcher, and in computer graphics, I learned a lot about things like how images are formed on cameras, illumination, the physics of how light interacts with objects. And I was actually shocked when I learned about how little the computer vision community today actually thinks about those things. But there's a reason for that, because once we have we can say that it's unfortunate, and maybe it is unfortunate. Once we have a general purpose toolkit, then it's a lot more important to think about how you're going to provide that toolkit with the data needed to accomplish your task than it is to figure out the particular intricacies of how that task works. And we might decry this, we might say that, well, it's unfortunate that the unwashed masses that don't understand the physics of how the system works can actually, get effective systems deployed. But I think that's actually a bonus, that the approaches in perception work so well that you don't need to be an expert on perception to build a perception system. And maybe one day robotics will be like that. Robotic learning systems will work so well that you won't need to be an expert on robotics to deploy a robotic system. And I really hope we can get there soon.
Ashish has raised his hand to chime in.
Yeah, yes, thank you. Thank you for having me and great talks. I think I'm so glad Danica brought up interaction word. I wish we had spoken about that a lot more. Tamim said, what is unique about manipulation? And I think interaction. And then Frank had brought up kind of, which I agree with, is that force, position, and impedance are simultaneously need to be modulated, right? While the object's mechanics is changing, in many cases, robots' mechanics is also changing, especially if you have soft hand or whatnot, right? So, so maybe is that the kind of unifying theme that Odd was saying? And then coming back to learning, if you're doing force, position, impedance, all have to be changed. And if you're focused on only control of pose, then we may not be able to achieve really good manipulation. I'm not saying every learning approach is doing just pose, but wouldn't we want to learn modulation of some combination of force, position, and impedance, right? And then it goes to design of the robot. The robot should be able to change those aspects. And then it goes to what Francisco knows as well as anybody in the human case, we are able to do that. Redundancy of muscles, the force control of the muscles, we are able to do that, right? So I'll pause there. I don't have questions specifically for people, but I think hopefully people can comment.
I totally agree. And I think that based on what you all are saying, we should also remember that, at least in humans, the hand is actually mostly a sensory organ, right? And so we need to blur the distinction between sensory and motor. And then it becomes like a closed active sensing, active perception type of situation where there's no beginning and no end. So we're not divorcing the control from the sensory. And that's how you generate these percepts of the actions that you're taking in the world, for example.
So let me just interject here very briefly, two questions from the audience. An anonymous person asks, how critical is a sophisticated sense of touch like that of humans necessary for future robot manipulation? And there's another post by Mosen, which is basically more a statement: without having tactile information, cutaneous, proprioceptive, it is impossible to manipulate soft and deformable objects with dynamic centers of mass. So this kind of goes into this, what's the role of sensing in manipulation, and how are we doing on that, and what do we need, I guess, in the future?
If I can maybe
go ahead, Frank.
Okay, yeah. I love Francisco's statement that grasping is not manipulation. Totally agree. It would be great if we can have an end-to-end system for manipulation, but I like to think about the task of rolling and cutting sushi, for example. Contrast this with some of the the problems in vision. To me, if you're trying to teach a robot to roll and slice sushi, you have to take into account positions, forces, compliance, and of course there's contact braking and unbraking, deformations. And I just wonder, how successful, how much data you would need to apply an RL algorithm for this. And I doubt there are simulators that are good enough to generate sufficiently accurate data for this. So the difference between using deep learning for recognizing cats from dogs and learning how to make and cut sushi is it's like a finite dimensional versus an infinite dimensional problem. And you know, the amount of data I think you need for an infinite dimensional problem is much greater. And so, you know, while it'd be great if it could get end-to-end learning, you know, I just, you know, for tests that are so complicated like this, it just seems it's inevitable that you have to break it up and use mechanics and models where you can.
Alberto.
Just wanted to add a comment, if that's okay. I know that I'm on the front row, but just as a reaction to the question on tactile feedback and how important it is to develop sort of manipulation capabilities or manipulation skills. The way that I think about it is that, to me, it sort of plays the equivalent role that a torque sensor plays when you put it at the end of an actuator, as well as an encoder, right? So when you design an arm, you want the arm to behave the way that you intended, right? And to do that, because the arm doesn't sort of, it's an ideal arm, you need to have PID control loops so that it actually does what you tell it to do. And these PID loops, right, sort of, I would say that they are at the essence, at the sort of the lowest level of interaction and motion generation. And from an evolutionary perspective, they're sort of much older than anything that has to do with the structure of our bodies, right? And to me, tactile feedback plays the same role with respect to contact and interaction, right? So we have tactile feedback. One of the key roles that it plays is so that the contacts that we use to transmit forces, they behave more like what we intend them to behave, right? So if we want contacts to slip, if we want contacts to stick, if we want contacts to sort of maintain a certain preload or a certain pressure distribution, you need some feedback there, because the mechanics, they're not going to play sort of nicely the way that you intended, but you can have some control loop to make them do that. And to some degree, you can think of tactile feedback as the tool that you use to simplify the dynamics of interaction, right? You have those control loops so that the thing that happens is closer to what you intended. Without those, it's just like a very noisy process. That's my take.
Matt.
Unmute. Yeah, I don't know if I'm amplifying or nitpicking, but I think the observation that attraction is important if you want to control contact is probably right on. But I wanted to point out something else, which is that, you know, humans do so many different things, and they do these things so well that you can find evidence for any opinion about what's necessary or not necessary. So, you know, if I wanted to argue against tactile sensing, I would say, well, look at a human using tongs. Look at a human using, you know, gloves that impede their tactile sensing, right? They're so good at it that they will find workarounds, and, you know, they may not be performing as well, right? There are compromises. But, you know, this always hits me when I hear somebody say tactile sensing is essential. Yeah, you know, at one level, yes, definitely we want to have tactile sensing. And I'm glad people are working on it, and, you know, and I hope that they give us something great to use. But don't think that we can't do things without it, because actually almost everything in robotics so far is done without it. And a great deal of what humans do is done without it as well.
Thank you, Matt, for bringing that up. I totally agree with you. I think maybe the root of the tempest in the teacup here is that, at least in my opinion, from what I've seen in the biology and the robotics, is that sensing is critical to learn, but it's not necessarily critical to perform. So a lot of times we are misled by, for example, a video that, you know, showing a person trying to light a match with an insensate hand and they can't do it. So if you actually look at, you know, at that case, that was the first attempt of the person trying to light the match with an anesthetized hand. However, if you give them time and you give them visual input and all of that, they'll actually learn it. So in fact, the somatosensory cortices in the brain are most of the time asleep. And they're actually just looking for salience, for trips, for events, and then something happens, right? But most of the time in a learned task, sensation is not that critical at all. But for learning, it definitely accelerates it. So there is a very nice continuum here of when we need tactile sensing or not.
Maybe if I can, oh, sorry, Matt, you were going to reply.
No, Matt's hand is still open. Go ahead, Sergey.
Oh, okay. I just wanted to chime in here because I think what Francisco said is actually reflects maybe some robot experiments that we've done too. We worked on touch sensing in concert with perception, with visual perception for a while, and it was initially very frustrating because we couldn't get a lot of benefit out of touch sensing on a lot of the tasks we were trying to do. And I think that kind of what I learned from a lot of those efforts is that really when you have multimodal sensing, it's very redundant, and that redundancy often is not beneficial if you're trying to do one narrow thing. So if you train up a robotic system to do a particular thing, it often really kind of almost doesn't matter once it's kind of mastered what it's supposed to be doing, what kind of sensing it has. But the sensing does matter a lot if you're talking about generalization, if you're talking about robustness and things like that. And in the end, the one place where we did find touch sensing in concert with vision to make a big difference is in generalization for robotic grasping, not for grasping any particular thing, but for generalizing over a broader range of objects. So the lesson to me from that was that you know, we should be thinking about these things as redundant. We're likely not going to see a huge amount of benefit in narrow domains, because in narrow domains, you know, as long as the information is there, a good enough learning algorithm can pull it out. But it might matter a great deal more when you're talking about robustness and generalization.
Yeah, I mean, maybe this leads to sort of a broader question to have us head towards the future. We can identify various bottlenecks, right? Tactile sensing might be one, having enough data might be one, having enough compute might be one, having the right robot might be one. So all of these components of a robotic manipulation system might be the bottleneck. Which one is the most critical one for us to work on, and wouldn't that depend on exactly what it is that we want to do? So this answer might even vary by the type of manipulation task that we want to tackle. Ashish had his hand up first.
Sure. I think kind of redundancy also brings up kind of a generalizability issue of not only what we sense, but also what we control. You know, sort of thinking about pose or position and force and impedance. We can get away with a lot with just pose control is easy to sense. But if you want to do multiple things, we may want to control. So then it goes to design of how are we designing our robots to control what are the knobs we are turning for learning or for any model base. And so if we want to do complex things, we may have to control, have more actuators, be able to do torque tracking, so on and so forth.
Somebody else wants to jump in here? If not, yeah, Tamim. And then Matt, you're muted, Tamim.
Oh, sorry. I have a specific question to Sergey. So for this task with the 40 hours training or data collection, also you mentioned that a lot of hard work has to be done before. Can you say something on how much of that can I use for another task actually, or for the same task on another object?
Sure, yeah. Well, what I actually said, maybe I didn't phrase this quite as precisely. A lot of hard work needs to be done during the process. A lot of hard work needs to be done by the robot. That's what I said. But yes, of course, a lot of hard work has to also be done to actually like build the whole thing. And the reason that we wanted to demonstrate this on multiple tasks is precisely to make the point that once you build the system, then applying it to multiple different tasks doesn't require all that human engineering. It requires some setup. Like this particular system that I showed, it actually doesn't use visual perception, it just uses mocap because it's focused on the physical thing. So most of the work that we end up putting into it, setting up each new task, is actually figuring out how to attach mocap markers so they don't fall off. Once we switch to vision, they'll go away.
This I understand, but I'm trying to figure out how much work must be done for a new task or for a new object. This was still why I didn't get it actually.
Okay, so what do we need to do to apply RL to a new task? Well, we need to define a reward function. We need to attach the mocap markers or whatever other kind of routine physical setup we have. I think that once, it's always difficult to talk about this with a research prototype, because with a research prototype, there's also a bunch of work that needs to be done, like when the finger breaks and someone needs to go with a screwdriver and repair it. So it's hard to disentangle from that. But I think if I were to imagine kind of productionizing it, what would probably be the bottleneck is actually task specification. And that's something that I do think requires more work. It's something we're working on. And basically, how do you make it so that instead of having to program an objective, you can just have somebody, show an example of something and figure it out from there. And I think that might actually end up being one of the bigger barriers to deployment of this stuff. And that's why we need more research there.
Thanks.
So I don't know, Matt, you had your hand up for a second. Did you want to actually say something?
Yeah, I don't know if it's useful or not. The original abstract for this discussion was something like, how long until robots are as good as people, and how do we get there? And you just now asked a question that's like, what's the bottleneck right now? And my reaction to those questions is, first off, I never have an answer for those kind of questions. And this leaves me thinking that maybe the goal of achieving human equivalence is so distant that it's just too early. It's like asking people who have discovered how to make a dugout canoe how long until they're building an aircraft carrier or a spaceship or something like that, So I'll just toss that out there. Maybe we're clueless because we're really just at the beginning of all of this.
Francisco.
Downer, sorry.
Yeah, so I love that question, because I think one of the things, back to your question, Oliver, where should we be, putting effort? I think what biology did the hard way was do brain-body coevolution for a long time. And then what humans have been doing, and as is often forgotten, at a meta level, I mean, our hands are no different from the fins of a fish, right? Structurally, they're not that different. It's what we had to work with, right? And so humans created and co-evolved the world with the capabilities of their hand. So we often look like great manipulators because we created those objects to be manipulatable by us. Just think of musical instruments. If you look at a clarinet, for example, it's actually driven by the limitations of the hand. And so we need to also think at a meta level of co-evolving not only the controller with the algorithm, with the plant, with the actual physical body, with the objects, with the environment. I mean, that's another way to think about where to go next, to actually start thinking more globally.
I completely agree with that point. And I want to put that point back, I guess, to the entire panel. Is that something that you guys all agree with? I mean, does Maria now need to put to start using learning or planning to study soft robots? Does Sergey now have to consider actually not just buying a robot but building one in order to make real progress? Is that really where we're falling short?
So you mean how to implement that brain-body coevolution in robotics? Yeah, I think that's something we have to think about, because above all, I'm biased, but when we have soft hands and they can have such a different designs, and still we can call them soft hands, that then creating creating the algorithms to make them work require really to take the design into account. But maybe we can also change the design based on what we find and what we want to do with the controller, with the planner. So co-evolving the control and the design can be very interesting. I don't know. I mean, there are efforts in this sense. So the co-optimization of design and control, but yeah, I think it's something we can definitely follow and try to achieve. Probably the other thing that we have to think about is that we are trying to build robots that manipulate stuff that was designed for us, as we are saying. So yeah, so we have to take this into account. We have to take into account that we want robots to do a lot of different things when it comes to manipulation, and we are capable of manipulating a lot of different objects, and that's the main problem of manipulation in robotics. When we come down to very narrow tasks, then we can find solutions, I think. But the problem is finding something general that is something that we all want to achieve. General manipulation in unstructured environments, and that's not difficult. And maybe a way to go is what Francisco was suggesting.
Mm-hmm. Thank you. Tamim.
Yeah, I think the problem is so difficult that that people working in this area should know about many things, about design, about control, but also about learning. So yes, Sergi has to learn about how to understand how to design robots a little bit more, and Maria about learning, actually, because this is really crucial from my point of view. I mean, the problem is not only a design problem, it's not only a perception problem, it's not only a learning problem, but it's a combination of everything when it comes to manipulation. And I think taking inspiration from humans for design, but also from humans in terms of strategies when dealing with open-ended environments and difficult tasks is also important. So I think, yes, we need to understand the different perspectives of the different sub areas which are important for manipulation. From design, from the human to design, to control, perception, and learning.
So since we just talked about Sergey, let's give him a chance to chime in here.
Yeah, I figured since two people took a dig at me for my ignorance of robot engineering, I should respond. But in all seriousness, the robot that I actually showed in my video was actually custom designed for that experiment. I have to confess that not by me, it was designed by my colleague Vikash Kumar. Interestingly enough, the thing that we had to consider most of all for the design was not how easy it was for it to do the task, but how robust it was, because every other hand we tried to use broke. In fact, we actually had a fire in the lab from attempting to use a commercially available hand from a company that I won't name after about an hour. So the main consideration for us was just something robust enough that we could run experiments that were sufficient to illustrate the generality of the method. That said, of course, there's no way to argue that, like, any hardware can do anything. Like, of course, you need to build something that's sufficient for the tasks you want to consider. But I think Maria makes a really good point, which is that if you want flexibility ultimately. So if you want flexibility, like, yeah, you can kind of have something that is tailored to the tasks you want to do, but ultimately it needs to be tailored to flexibility. Like if you want to do lots and lots of things, you need flexible hardware. So you can't be completely dumb about how you build it. But I do think a lot of the burden actually is on the control system ultimately. So you can't just throw anything at it. You can't just throw any bag of nuts and bolts at it. But the controller has to do a lot of the work.
So we have to almost come to a close here now. Maria and Frank have raised their hands. I would like to ask you to try to be brief in your comments. Maria.
No, this is a little bit aside in the sense that we want to learn from humans how to build robots and make them work. But then what Danica said before, it's important. We want robots to work with humans in the very end. So we have to come also to that part, like acceptability, the fact that humans need to understand how those robots work. So we have also those problems to consider. apart from being able to actually build robots that manipulate stuff in a flexible way.
Frank, you have the closing comments here.
Gosh, that's a lot of pressure. Yeah, I just wanted to just go back to Ode's question. You know, I've been thinking about it. It's a pretty deep question about, you know, is there a continuum of between soft and hard? And I think it kind of goes back to, you know, Maria's comment about, you know, this work on co-optimization of motion and control and design. You know, to do that right, I think we do need some sort of this new type of model, you know, that encompasses soft and hard in a continuum fashion. That we can then, you know, use that model to try to come up with optimal designs and optimal controls at the same time. So I just wanted to point that out.
Great. So thank you very much. I think we have to come to a close now. I would like to first and foremost thank all the panelists in the front row. You know, we haven't seen each other in a very long time. It's been fantastic to see all of you on one screen at least. And apart from that, I think we had a very, very inspiring discussion. We touched upon many, many issues. Obviously, we were not able to answer the ultimate question, but hopefully we've triggered in our audience some new ideas that ultimately will lead to us answering the question. I would like to thank Osama and IFRR for organizing this series of events. And I would like to apologize to all the members of the audience who asked questions through Slido that I was not able to incorporate into this time. But I think many of the questions that were asked, I didn't bring up explicitly, were touched upon by comments of people from the panel and the front row. So I hope that everybody goes home with a sense of reward from this interaction. Thank you all so very much. And let me finish by pointing you to the next event. The next installment of this colloquium will be on task and motion planning. Thomas Lozano Perez, which Matt Mason mentioned in his presentation as the robotic inventor of the configuration space, will be the speaker, and Chris Hauser will be the moderator. So we hope to see you all again there at this next event. I think it's in 2 weeks. Thank you very, very much to everybody. Thanks a lot to the audience for hanging in for so long. Yeah, let's solve manipulation in the coming years.
Thanks, Oliver. That was fun.
Thank you. Bye.
Thank you so much. Bye-bye.